Hello everyone, I'm Sachin. Today I'm going to talk about efficient situation scheduling of graph model workloads on single chip multicores and GPUs. Well, coming to the topic, introduction to graphic workloads and scheduling. Graphic workloads are characterized by irregular data access patterns and complex dependencies. Efficient scheduling is critical to maximize performance and resource utilization on hardware platforms. This presentation explores the situational scheduling techniques tailored for the single chip and multicores and GPUs. So these graph workloads are categorized by irregular access patterns. Like RAID access patterns are characterized by these graph workloads, and there are also complex dependencies which also are characterized by these graph workloads. Efficient scheduling is critical to maximize performance by using these graph workloads, and also resource utilization is also used on the both the efficient scheduling and resource utilization are used to maximize performance on these hardware platforms. Uh, During this in this presentation, we can also explore how the scheduling techniques are tailored for single core and multi-core GPUs. Mm. Coming to challenges in graph workload scheduling, irregularity and data dependent execution make load balancing difficult. Traditional static scheduling often leads to underutilization and bottlenecks. Hardware heterogeneity and limited memory bandwidth further complicate scheduling strategies. So there exists irregularity and data dependent execution, both of which make the load balancing difficult. There are also traditional static schedulings, which often lead to underutilization and bottlenecks. So the static scheduling, it doesn't it 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 underutilizes and also creates bottlenecks too. So the heterogeneity and limited memory bandwidth will also complicate. It also further complicate the scheduling strategy more. Single chip multi-cores architecture overview. Single chip multi-cores consists of multiple processing cores sharing cache and memory resources. They enable parallel processing but require efficient workload distribution. Memory hierarchy and inter-core communication are key factors affecting scheduling efficiency. So, in this single chip multi-cores, a single chip which consists of different cores, like this octa-core, dual-core, quad-core processors, which we see in every system nowadays. They in this they all they share cache and memory resources in a single chip. They all share cache and memory resources. Due to this, it having multi cores, it enables parallel processing, but it requires efficient workload distribution to handle the parallel processing. Memory hierarchy and intercommunication are key in affecting the scheduling efficiency that this single chip multi cores has. Coming to GPU architecture and limitations for graph processing. GPUs provide massive parallelism with thousands of cores of optimized for SIMD execution. The memory model favors data parallel tasks, posing challenges for irregular graph algorithms. Efficient scheduling on GPUs must consider warp prevention and memory coalescing. So these GPUs provide massive parallelism. These have thousands of cores optimized for this execution. So there are, yeah, massive parallelisms are being done using the GPU, and there are in the GPU there are thousands of clocks optimized only for this execution. Uh, the memory model of the GPU favors data paralleling tasks, like posing challenges for irregular graph algorithms. Like this is specifically designed for data parallel tasks. Well, for irregular graph algorithms, it may be it may pose some challenge or being difficult. Efficient scheduling on GPUs, we must consider warp divergence and memory coalescing. So memory coalescing warp divergence must mu- to have them efficiently on GPUs, we must consider these two: memory coalescing and warp divergence. Coming to situation scheduling concepts and goals. Situation scheduling dynamically adapts to workload characteristics and hardware states. The goal is to improve workload balancing, reduce latency, and maximize throughput. It involves real-time decision making based on workload and system conditions. So how this situation scheduling works is it automatically dynamically adapts to workload characteristics and also hardware shares existing. The main goal in this situation scheduling is to improve the load balancing and to reduce latency and to maximize the throughput which exists. It involves real-time decision making, like which is done in real-time bias on the workload and and which also depends on the workload and system conditions. Techniques for efficient scheduling on multi-cores. Work stealing and dynamic task partitioning can help balance load across cores. Fine-grained synchronization minimizes idle time and communication overhead. Adaptive scheduling algorithms respond to runtime workload variations for better efficiency. So, uh, there is also work stealing and dynamic task partitioning, which help in balancing the load across the entire across the cores. There is also fine-grained synchronization being done, which minimizes the idle time and communication overhead. Uh, if there is fine grained synchronization being done, idle time is reduced and communication overhead are also minimized. Adaptive scheduling algorithms can respond to runtime workload variations for better efficiency. So these adaptive scheduling algorithms, they can use it to respond to runtime workload variations for better efficiency. Uh, Techniques for efficient scheduling on GPUs. Warp-aware scheduling assigns tasks considering warp execution patterns. Priority and preemption strategies help address irregular graph traversal issues. Memory-aware scheduling optimizes data locality and reduces bandwidth contention. So these warp-aware scheduling tasks, uh, consider they are considered for warp execution patterns. Their priority and preemption strategies help address these irregular graph traversal issues. If there are irregular graph traversal issues, this priority and preemption strategies help with that. Uh, Memory aware scheduling optimizes data locality. So these aware scheduling, the which is being done through the awareness of memory, this optimizes data locality and also this reduces the bandwidth contention. Comparative analysis of scheduling strategies. Dynamic scheduling offers flexibility but may incur overhead. Static approaches are simpler but are less adaptable. CPU-specific scheduling exploits massive parallelism but must handle warp divergence effectively. Combining multiple strategies can yield balanced performance improvements for diverse workloads. So, in this comparative analysis, if we see that dynamic scheduling offers flexibility, but it may have overhead. So we must consider the overhead when we are trying to use dynamic scheduling uh, in the name of flexibility. Overhead may be an issue too. Uh, Whereas coming to static approaches, they are simpler, far simpler, but are less adaptable, which may not have the enough flexibility or the adaptability required. So we may choose between the both of them for our which suited to our requirements. GPU specific scheduling explores massive parallelism, but must handle the warp balance efficiently. So which are exploit GPU specific scheduling, they have massive parallelism, but they must warp divergence is very crucial in it, and they must handle it very effectively. So combining multiple strategies like this GPU specific exploits and also dynamic scheduling and static schedule approaches, this may improve yield the balanced performance and also improvements for diverse workloads too. There are future research directions and research opportunities. Developing hybrid scheduling models that leverage strengths of both multi-cores and GPUs, incorporating machine learning techniques for predictive and adaptive scheduling decisions, enhancing hardware support for finer grained and more flexible scheduling mechanisms. Um in the future, we can develop hybrid scheduling models which can leverage the strengths of both C monitors, multi-cores, and GPUs in a combined way by incorporating machine learning principles and techniques, predictive and adaptive scheduling decisions. Like by developing technology by using advanced learning techniques, we can use for both predictive and adaptive methods by using the machine learning techniques in the future. Uh, we can enhance the hardware support for fine-grained and more flexible scheduling mechanisms too. Coming to conclusion and key takeaways, efficient situation scheduling is better for optimizing graph workload execution on single chip multi-cores and GPUs. Tailored approaches addressing hardware and workload characteristics significantly improve performance. Ongoing research is essential to handle the increasing complexity and scale of graph-based applications. So a conclusion comes to like if efficient situation scheduling is definitely the most important for optimizing this graph workload on the single core and multi-core GPUs. So if this is not properly done, the workload may be increased or it may not be processed properly. So tailored approaches addressing hardware and workload characteristics can significantly improve performance. So tailored approaches for the single core and multi-core GPUs, I mean for the hardware, tailored approaches for the particular hardware, maybe the GPUs, the chips. This they directly influence the workload characteristics, and they also help in aiding in significantly increasing the performance. There is definitely ongoing research being done to handle the increasing complexity and also the scale of the lab-based applications. So this is a very core technology, like efficiently handling both of the graph workloads on this single chip multi-cores and GPUs. If we are able to combine both of these and use it in a regular life, it may also reduce the workload by a lot and also increase computational processing power by a lot too. So it's a very new emerging technology as technology is being developed for a long time. GPUs are being updated year by year and also coming more into trends. So this helps in making more impact on the programs and also increases computational power overall. Uh, Thank you for listening to the presentation.